Let's keep cruising through here and talk about something that you're going to want to take another class so you can spend a whole semester learning. That thing is what we call regression analysis. Regression analysis is one of the most useful, powerful, and frequently used tools in all of statistics. It is vital that any college student spend their life studying regression. It is an extension, it's related to correlation, but it's way better. If you can think of what regression does this way. If we take some variable and we find its mean, we get a number. So we say, okay, what's the mean of SAT scores of all universities in the country? We get a number. What if we want to compare SAT scores for students and their GPA when they get to college? We want to see if the SAT score you got when you were in high school is a predictor of how you're going to do in college. Well, now we have two variables. If we want to squish these variables together, we want to find the mean of the two variables at the same time. I know you're thinking, why would I ever think to do that? Well, that's a very good question, and it's one of the most exciting things in life. Okay? If we find, so we have a whole slew of numbers, and we take the mean, and we get a single number. If we take two sets of numbers and we find their mean together, what we get is a straight line that is the mean of those two numbers. I know, it's kind of great philosophy and statistics wrapped up in one. So what we're going to do with regression is create a straight line, and that straight line is going to let us take a value of one variable and use it to estimate or forecast the value of another. So what we want to do, for example, is come up with an equation that would let us plug in someone's SAT score in high school and use that to predict what their GPA in college is going to be. Okay? Usually we do much more complex things where we take 10 variables and we use them to predict. So if once you become an econ major and then you get really good at stats and you want to get a real job, which is econ's the only business major that gets you a real job. If you have an econ major and you have all your stat background, you can get hired by a company like Caesars. And what they do in statistics department at Caesars is things like figure out the characteristics of a guest. Figure out, hey, if this guest has, if they do this and they play this game and this is their game and that's what they play, or they go to shows and they eat at these restaurants and they come here this often, what's the right room rate? Is there some room rate which will get them to come here more often and spend more money? Well, companies like Caesars believe that it's true, that they can put in characteristics of individual people who come to their hotel, and from those characteristics find a room rate which will cause that person to be more likely to come and more likely to spend money if they do. So there's some people who, they're cheap. When they come, they don't spend any money, and that equation is going to make them pay a high room rate because they don't spend money on other things. Other people who spend lots of money on other things, and particularly in certain patterns, are going to get a low room rate because. Okay? A hotel like Caesars, it has 2,000 rooms. There might be 200 or 300 different room rates being paid because you did a regression analysis, and that regression analysis allows them to try to do what we call revenue management, which is try to get the most possible money out of each one of their guests. We can argue about whether they really know what they're doing and, the old Vegas way versus the new Vegas way, but it's undeniable that all of these big casinos have these departments that use regression to try to optimize their revenue. And they pay a lot of money to do it. Anyway, so if you took math, and you all should have taken math to get here, mathematicians write out line equations like this, where m y equals mx plus b. M is the slope, b is the y-intercept. So a mathematician would say, we'll call that point there b, and then there's a straight line, that's a straight line, and it has a slope of m. Statisticians, because we have to do things our own way, use the equation y equals a plus bx. So we're going to draw a line that looks like this, where this point right here is a, and the slope of the line here is b. Okay? So we're going to say y equals a plus bx, or alpha equals y equals alpha plus beta x. Okay? And some other terminology that goes with that is independent and dependent. In this equation, x is what we call the independent variable. It's your SAT score. It's what we know. We know that your SAT score was 1200. What we want to figure out is y, and we call the thing we want to figure out the dependent variable. So the independent's what we know. The dependent is what we want to figure out. This would be, in this case, your college GPA. Okay? Exciting? So independent variable is the thing we know. It's the thing we want to plug into the equation and figure something else out. Dependent is what it is we're trying to figure out. So we have, for example, also a lot of regression equations where all we put in here is what year it is. So I have a colleague who many years ago, badly, but don't tell him that he did it badly, tried to figure out how big the airport needed to be. The airport hired him to figure out how big the airport needed to be. And he did a regression where he took all the prior year's data and he looked at how each year and how many people came in. So he used the year it was to predict the number of tourists, and then he could stretch it out in the future. So maybe he used, he didn't, but let's assume he could have used data. Maybe if he did this in year 2000, he could have used data from 1970, say, to 2000. And put in every year, the number for the year, put in 1970 and 1971 and 72. And over here, put in how many tourists came. And then use this regression to try to predict how many tourists would be here in 2010. Or how many tourists would come in 2020. Okay? So I use this old data here. Old data on how many tourists come and what year it is. And then I can put future years in here and try to predict future number of tourists. Now, he did badly, and that's why the airport looks so stupid. But doesn't mean it wouldn't have worked if he had done it right. So let's look at some numbers here. We have an x and a y. So x is 2468, y is 3456. If we look at those numbers, what we see is that every time x goes up by 2, all right, every time x goes up by 2, y goes up by 1. X goes up by 2. Y goes up by 1. So it's a perfect relationship where any change in x, y changes exactly half as much. We agree? Okay. So from this, we can find a correlation between these two, right? So we have the mean of x and the mean of y. Boom, boom, boom. Each point minus its mean, multiply them together. We just did this on correlation. We find a covariance of 2.5. Since it's a positive number, that tells us it's a positive relationship, but the direct relationship at the 2.5 doesn't mean anything. We can do the calculation of little r, the correlation coefficient, and voila, to speak French, it equals 1, which means there's a perfect relationship here, which we knew, okay? We knew that that would be the case because every change here of 2 gives us a change of 1. That's perfect. Now, remember that to find the little r, we divide through by the standard deviation in x and the standard deviation of y. Let's just change this equation a little bit. And I'm not going to tell you how we know to do this because I know you'll be so excited to find out why we do this that you're going to sign up for 262 next semester so you can study more regression. So we're going to change S of x to S of y to S of x times S of x, the standard deviation of x twice. Okay? And if we do that and do that math, we come out with a half, which we know is what this is. 1 is half of 2. 1 is half of 2. Here's 2. Here's 1. 1 is half of 2. Ooh, we get a half. Okay. The other thing to remember in a brain, because we all have brains, is that the standard deviation of x times the standard deviation of x is the variance of x. Do we remember that? It's the variance of x. So, this is the covariance of x and y divided by the variance of x. Okay? And this is how we find the slope of a regression equation. I know, you're like, we're looking for this. We want a y equals a plus bx. Okay? Well, we just figured out how to find b. So b is a half. So we know that y equals a plus 0.5x because of that calculation we just did. Now we need to find a, and we're just going to find a by doing some silly little algebra. I know you hate algebra, but that's what we're going to do. We're going to put in the mean of x and the mean of y, x bar and y bar. We know b is 0.5. We know what that number is. We know what that number is. We know what that number is. And we can solve the equation for a. So let's go up here now. I did that, I think. There we go. Because a regression line is actually finding the mean of x and y together in two-dimensional space, it's a two-dimensional mean, it means that the line has to go through the mean of x and the mean of y at the same time. So we have this y equals a plus bx equation. We want to find x bar and y bar in here. So we put in 4.5 and 5, which from back here, that's 4.5 and 5, the mean of x and the mean of y. All got that? So here's the mean of my mean of y, mean of x. That's x bar. That's y bar. The mean of x and the mean of y. That's b, which we just figured out how to calculate. And we do some algebra, and we find that a equals 2, which means we have this equation right here. So what it says is, if you know x, you can put it in this equation and find y. So let's go back. We have an x of 2 and a y of 3. Do we all agree? X is 2, y is 3. Put 2 in here. A half of 2 is 1 plus 2 equals 3. Go back again. X is 4, y is 4. Put 4 in here for x. Half of 4 is 2 plus 2 is 4. Isn't that beautiful? Any value of x I put in here, out pops the value of y. That only works because correlation is 1. If the coefficient weren't 1 or -1, it wouldn't work quite so well, but we'll see that here in a second. Okay? So again, in every case, I can put in x and y. I can put in x and out pops y. It's perfect. It's beautiful. It's perfect. It's math. Math is a miracle. Okay? So again, this is a perfect relationship. What happens if it's not a perfect relationship? How do we judge statistical things? Because obviously, two people with exactly the same SAT score in high school are not going to have exactly the same GPA in college. Some people with really high SAT scores do badly in college and they get bad GPAs. Some people with bad SAT scores still get good GPAs, but mostly the higher your SAT score is, the higher your GPA will be in college. So here's an example. I took 4 softball teams. These are 4 actual softball teams from the fabulous Mountain West Conference. And I put down the number of wins they have and their batting average. Batting average usually has a decimal point, .300, but I took the point off because who wants to deal with the decimal point thing? So we had a team in the Mountain West that had 24 wins with a 300 batting average, a team with 36 wins that had a 320 batting average, a team with 30 wins that had a 260 batting average, and a team with 30 wins that had a 280 batting average. So that tells us that the team with the highest batting average had the most wins, but the team with the lowest batting average didn't actually have the fewest wins. Team with a medium batting average had. So this isn't really a very perfect relationship. It's a pretty bad relationship. And in fact, if we did this again and we put their pitching statistics in, pitching statistics are a much better predictor of winning than batting average. But let's do this anyhow. So we have the mean number of wins of these teams is 30 wins. Their mean batting average is 290. And then we have standard deviation of y. And this is the standard deviation of x. How do I know that's x and y? This is x, and this is y. How do I know that? Because I know the batting average, and I'm trying to predict wins. So this is independent and dependent. Independent. Dependent. X and Y. I know X, I'm trying to predict Y. So let's say we had a fifth team in the Mountain West and they batted 240. How many games should they win? Well, what I want to do is create an equation, stick the 240 batting average into that equation, and have that equation come out and predict how many wins they should have. So I can do this. I'm going to find correlation. I'm going to find R, right? I know that R is not going to be 1 because it's not a perfect relationship. It's going to be less than 1. So here I get a covariance of 30. That tells me this is positive, but the 30 direct relationship, but the 30 doesn't mean anything. I do the math. I divide by the standard deviation of x and the standard deviation of y, right? I'm going to take 30 and divide it by 4.24 and 22.36. I'm going to get 0.3164. That's really a bad correlation. There's not much correlation here. Okay, it's 0.31. It should be close to 1. It's much closer to 0 than it is to 1. Tells me it's not a very good correlation. The batting average isn't a good predictor of number of wins. Okay, so then I take the covariance, divide it by the standard deviation of x twice, the variance, and I get 0.06. which is the B of our equation. And then I solve our equation. I put y bar and x bar into our equation. I solve that equation, and I get an A of 12.6, and I get this equation right here. Okay? So what I have is a regression line that looks like this. I put their batting average here. I put the number of games they win here. I put a point right here, and that point is 12.6. And then there's a line that goes up, and it says for every 1 point I get an increase in my batting average, I win 0.06 games. So 1 point increase in my batting average, I'll win 0.6 more games. I know that's hard to do. 10-point increase in my batting average, I'll win 0.6 more games. 100-point increase in my batting average, I'll win 6 more games. Okay? So now I can put this batting average in here. If I think this team batted 240, I can put 240 in there, multiply times 0.06, add 12.6, and that will predict for me how many games that team should win. Yes? So 6 times 24 is 14.4 plus 12.6. And my equation says 27 games. So if your team has a batting average of 240, my equation says you should win 27 games. Let's go back over here. Well, 240 batting average is below this and below that and below that. So 27 makes sense there. but it doesn't sort of make sense there. But we knew this wasn't going to be a very good regression anyhow. Okay, so my number of wins equals 12.6 plus 0.06 times my batting average. Okay, and we then know that the line starts at 12.6. That's what that A is. That's where the line starts. Sometimes it has an individual meaning, but it really doesn't here. It just means the line starts at 12.6. And for every 1 point increase in batting average, I get a 0.06 increase in number of games I won. Okay? Not really a good equation.